I'm going to talk about a few different strands of work. So I think I've got, someone had you have the misfortune of dealing with me for 2 hours. So I'm going to break this up into 2 parts. The first one is going to be just one work through example of algorithmic bias in a live algorithm that is unfortunately still up and running and affecting lots of decisions for lots of people. And then try to take away some lessons for thinking about that kind of bias, which I think is a very common one, not just in health, but in lots of other fields. And then proposing a little framework that has at least helped me think through it. And then in part 2, I want to maybe paint a more optimistic picture of algorithms that can actually do better, that can fight against bias rather than just not scaling it up and augmenting it. And throughout this, I'm going to highlight 2 kinds of work. So there's one kind of work that I think will be very familiar to all of you, which is publishing academic papers. And so that's a couple of these strands of work or papers. But I think as I've done some of this work, both on bias and more broadly on applying computation to medicine, it's become more and more obvious that there's some sort of translation that's needed, like whether the papers are identifying a problem in the world or highlighting a gap in the world that needs to be filled. There's just a bunch of translational stuff that came out of some of the academic work where the venue wasn't so much another academic paper, but an actual thing in the world. And so I wanted to highlight some of that work as well. Okay, so let's dive in first to, I just, without much preamble, I sometimes think it's easier to engage with a concrete example. So I'm just going to go for the example first and then step back and generalize later. So this is an example of a very widely used set of algorithms in the healthcare system. And the way to see how these algorithms got so big and started operating at such scale is to tie it to the thing that health systems are doing. And so this largely started under Obamacare, but the healthcare system basically went from a model where you walk in, you get some treatment and the health insurer pays you for that thing, to a model where the health system is paid a flat fee for you to take care of you for a year. And then no matter what happens to you, you kind of they take care of you. And so this, shockingly, got the healthcare system interested in doing more public health and population health stuff rather than just delivering treatments to the person in front of them. And so now when health systems think about delivering care, they think about a population of patients where they're just responsible for the health of that population of patients, both their health and their costs. So that was the major, if you want to think about the big change of Obamacare, this is it. It's now health systems are thinking about populations rather than individual patients. And when you're responsible for a big population of patients, you know that some of them are ticking time bombs. So some of them are going to get sick. They have chronic illnesses, they look okay today, but they're heading for a decompensation of that chronic illness tomorrow. And it would be really, really valuable to know which ones are going to get sick. Not necessarily the ones who are kind of just getting very, very old and we know that they're going to get sick and we can't really do anything about it. But the people who have chronic illnesses like heart failure, if you take your blood pressure medications, if you adhere to a good diet, if you do all the things you're supposed to do, you can stay out of the hospital, stay healthy. That's good for you, that's good for the healthcare system. So those are the kinds of patients that we're talking about. People who look okay today, but they've got these chronic conditions that can push them over the edge tomorrow. And so what healthcare systems have done to deal with those kinds of patients is called care management or complex care management or whatever. But basically, the way to think about these things, which is something that all health systems are doing both in the US and outside the US, is it's a little bit like a VIP program for these kinds of patients who have complex needs. There's one phone number that you just call and you get a human, and that human is going to help you with whatever you need. If you need a primary care appointment, you will get it the next day. If you need extra help with your medications, refill, someone to come to your house and look at an injury, it's all just taken care of. There's one phone number, and they want you to call it because they want to keep you out of the hospital. So there's a lot of evidence that these programs help when we're thinking about the control of these chronic conditions, when we're thinking about controlling costs and keeping people out of the ER and out of the hospital. So this is all kind of like a win-win. People stay healthy, The healthcare system saves money. It's kind of like, it's great. So that's population health management. The only problem, as you can imagine, is that these programs are not cheap. So you need a team of these like highly trained nurse practitioners to come and go to your house to answer your questions. You need to set aside some spare capacity in your primary care clinic so that you can get people into those slots. All that stuff is expensive, and targeting that program to the people who need it and not giving it to people who don't is really, really important, because you just can't do it for everyone. There's a scarce resource, so it needs to be targeted. So you can already start to see where the algorithms are going to come in, but it's kind of important to distinguish between, or to just call out one problem, which is that the goal, and if you look at the marketing, the promotional materials that all these companies that make the algorithms put out, what they say is like, oh, we're going to find people who are going to benefit from this program. And that is a hard problem. Like, heterogeneous treatment effects are very hard to do properly, especially given the data constraints in the healthcare system. So that, as stated, that is a very hard problem to solve. So there's a critical simplifying assumption that all of these algorithms make, which is not an unreasonable one, which is that if we knew who was going to have their heart failure flare up, we have things to prevent heart failure flare-ups. So we're going to predict who's going to have those things happen to them so that we can target today. So that makes a very hard statistical problem into a much easier problem that's a great fit for all sorts of ML type stuff. So that's kind of like the way to think about what these algorithms are doing. So basically, this is the opening where algorithms are coming into the healthcare system, and the scale is just enormous. So we're going to be talking about one piece of software sold by one company, and that piece of software is used to make decisions in a way that I'll show you in a second for 70 million people every year. And if you look at the family of algorithms that work just like this algorithm, it's basically that the majority of the US population is being run through these algorithms every year, and it's shaping some really important decisions. So, what all these algorithms do is find people, look at people's data today, and yesterday, like going back as far as we have data, and make a prediction on who's going to get sick tomorrow. And the way they do that is they look at over the next year, starting today, we're going to make a prediction on, we're going to aggregate up all of the costs that people generate by coming in and seeking healthcare. So those ER visits that we're trying to prevent, they generate costs. The hospitalizations that follow from the ER visit because you need your water taken off with intravenous medications in the hospital when you have heart failure, that's generating expenses. So they're just totaling up all the expenses over the year from today until next year. They're making a prediction on that cost trajectory, and then they're prioritizing who's going to get help today based on that prediction for tomorrow. So we were interested, because of the way that this problem was set up, and because of that, prediction that all these algorithms are making, we already had some suspicion that something was not going to turn out to be totally right. And you can already sort of see why, but I'll come back to it in a second. And we wanted to know, are these algorithms biased in racial ways and in other ways? A really important thing that, in retrospect was clear, but took us a long time to figure out and put our finger on, is that when you're studying bias, of course, you need to have a good definition of bias to work with. And this turns out to be, kind of a problem. Now, we know this is a problem from the literature on all of these different bias metrics, because they can't, even though on their face they all seem pretty reasonable, they can't all be simultaneously satisfied. So just from that literature, we know that we need to make some choices about, which bias metric are we going to use. And I think that, when I was first reading this literature, I found it incredibly confusing because they all seem pretty reasonable, and yet they can give you completely different conclusions on whether or not something is biased. So when we were thinking about, okay, well, what is bias? What is unfairness in this setting? I think it was really, really helpful to actually take a step back from all of the literature and just really think about the context and think about, okay, what are the consequences of bias predictions. Who does that harm? What are the things in the world that happen differently because a prediction works one way or another? And knowing how that algorithm is used, I think for me introduced a lot of clarity in trying to figure out like how to actually define bias. And so I want to just, that's why I'm going to take a very detailed look at the context in which this particular algorithm is being used. The broader lesson, for better or for worse, is that there's probably no one metric that's going to work all the time. And even worse, you actually need some domain knowledge to understand how to quantify bias and how to measure it and how to determine if something is biased. And that is pretty labor intensive and does require like some investment in understanding how these algorithms are used. Okay, so let me tell you about the algorithm that we studied. So it's trained on a national data set. So the company that makes this algorithm has access to a big national data set of insurance claims. And they train an algorithm that takes in all of the prior insurance claims from a patient and makes a prediction about that patient's cost over the next year. Then that software, which is just the weights from basically like it wasn't quite just a regression, but it was pretty much just a regression. Those weights get sold to health systems along with like a little bit of software that makes the integration somewhat easier. Okay, so we're going to get data from one academic hospital in Boston, where I used to work. And we're going to get data specifically on the primary care practice of that hospital. It's about 40,000 patients. It's about 12% Black. And basically, like the algorithm is used to score that entire population a couple of times a year, and it just generates, an action, which is basically over that entire primary care population, who do I enroll in this extra help program, this high-risk care management program? And this is, as we've done follow-up work and seen other health systems using this and similar algorithms, this is basically like what all of these health systems do. So in particular, you can imagine this algorithm generates some distribution of risk scores, and there's some very high-risk people in the right tail. And basically, in the health system we were studying, the top 2% just get fast-tracked into the extra help program. So they're kind of automatically enrolled in that program. They get access to all of this extra help, the house calls, the extra slot, everything. About the next half down, there's like a human-in-the-loop kind of configuration where that triggers 3 times a year the people in this range of the algorithm risk score. They get put on a list and they get shown to their primary care doctor, along with a little bit of contextual information. So it's like, here's your patient, Mr. X. Here's their algorithm score. And here's some other data, like they have heart failure. They have been in the hospital 3 times over the past year, like a couple other things. But it's basically like a big spreadsheet of like all the patients that are in this range. And the primary care doctor will just check off like, yes, 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 no, this person probably wouldn't benefit. And so that's the kind of like the next tranche of the distribution. And everyone else gets screened out. So there's kind of like an automatic screening out of the bottom 55% of patients. So in a very real way, 3 times a year, this algorithm is determining how people get treated with respect to this decision of who's getting extra help with their chronic conditions. Let me pause there and just see if there are any thoughts or questions so far. Yeah?
Do the primary care physicians get checked if they're calibrated or any sense of, like, suppose, I was just thinking, what if they don't like a patient is rude to them, stuff like that? Is that counted out?
Yeah, it's an interesting question. I can answer it somewhat indirectly, which is to say that essentially, if you look at how the physicians are responding to this list, they're basically following the algorithm score. So they're not really adding too much plus or minus to that like list that the algorithm is generating. And if you can imagine, it's kind of like primary care doctors have a really hard job. Their main job is like taking care of patients, but increasingly they're being asked to do all this other stuff, like screenings, see if your patient benefits from this, look at this list, do this thing, write all these emails. So you can very easily imagine how 3 times a year I get this big list and it's like, okay, what do you want me to do? I'm not gonna sit down and go over this list for 5 hours, which is what I'd actually need to do if I wanted to add value. So they're not doing too much beyond what the algorithm is already suggesting. Any other, I should have said my core seminar audience is economists who just like interrupt me, so I'm not used to pausing for questions, so you should just, yeah.
I think you said earlier that this was a regression. So can you say just a few words about what the features are that are being regressed on?
Yeah,
How
so,
are people being represented?
so the training data comes from insurance claims. And insurance claims are basically like you go into a hospital, the doctor says, oh, you have indigestion. I'm going to give you a prescription for omeprazole. That generates a claim because you went into the doctor's office. It generates a bill from the physician. Those things have your diagnosis of like, acid reflux. It also has your history of like, if there's other diagnoses that are relevant, like, oh, you also had a fracture in your clavicle. And so that'll make its way on there because the doctor says it's not refracturing your clavicle. And then you'll see the medication that you were prescribed. So any kind of transaction between the patient and the healthcare system generates like a little thing in the record. That's this very complex time series of medications and diagnoses and procedures and labs and things like that. It's not the result of the lab. It's just the fact that a lab was done, because it's not electronic health record data. This is just the financial transaction data. So all of those things get aggregated up into features. And so basically like a feature would be, how many times were you prescribed omeprazole over the past 3 years? So that's like and then it's like, how many times did you see a primary care doctor? How many times did you see a cardiologist? And then how much did you cost? And like all of these other things. So all of that, this complex time series of bills and transactions are featureized. And then those things are put into kind of like a regression type thing.
How does the false positive and false negative?
Sorry,
How does the false positive and false negative rates of this happen?
Sorry, there's some sort of, say it one more time.
How does the false positive and false negative rate of the algorithm?
So let me get into that in a second, because I think the false positive and false negative rate is itself kind of an interesting question, because what is the gold standard here? If you want to talk about false positives and false negatives, you have to have both the test and the gold standard. And I think that in some ways, the whole complex part of this enterprise of diagnosing bias is figuring out what the gold standard is. So let me talk about that next, and then I'll come back and see if I answered your question. Okay, so given everything that we talked about as far as the context and how the algorithm is being used, let's go back and try to define racial bias. So what we've seen is that patients with the same score are treated the same way. They get the same level of access to this extra help program. If they're very high risk, they get fast-tracked in. If they're in the bottom 55%, they're screened out. In the middle, there's this kind of intermediate solution. And so basically, let's do the thought experiment. Let's say, okay, if we have two patients whose scores are the same, their future health needs should be similar, because that's what this program is doing. The decision is, who needs help so that I can allocate help? So the neediness of these two patients with the same score should be the same, because they're being treated the same with respect to this extra help. And of course, the color of their skin should not matter. So what we're going to look at is a variety of measures of health, that's H, conditional on that risk score. And we're going to be comparing primarily black to white patients, although we also do a bunch of other comparisons in the paper, but the main one of interest here is the black-white difference. And we're going to use a bunch of different measures of H, because that's one of the luxuries of working in electronic health record data, which is what we had access to, is that not only do you have this algorithm score, you also have this very rich set of data on what happened to the patient and what their outcomes were. And I wanted to just flag that, because I think that's, there are a bunch of problems working with these algorithms in other settings, like in criminal justice. You have to get someone to hand over the algorithm, and then you have to link that to all these other things. And it's actually really hard because no one is obligated to hand over the algorithm to you. And in fact, companies can often block any scrutiny of those algorithms in criminal justice systems. They've been quite successful at doing that. In health, they're just sitting on the server. And so if you can access that server, under an ethical research agreement or whatever you need to do the research, you get the score, you get the inputs to the score, you get the output of the score, you get all of these other like rich data. So this is a really nice place to study algorithmic bias in general, if you can get access to the data, which I'll come back to in a second. Okay, so here's the paper in one graph. X-axis is bins of algorithm score. So we've just kind of binned the score into percentiles. Y-axis is one synthetic measure of health. So this is basically a count of how many chronic conditions have flared up over a year. So the algorithm makes its prediction at T0. We look over that next year and we just count up, okay, heart failure visit +1, emphysema, ER, like hospitalization, +1. So we just kind of count up all of these chronic conditions that flare up as one of our measures of health. So that's on the y-axis. And then we've separated out black and white patients, with the black patients in purple and the white patients in gold. And what you can see is that no matter where you are in the algorithm score distribution, the black patients have worse health than the white patients over that next year. So the algorithm views them the same, that's like the vertical line, and the white patients go on to have better health than the black patients over that next year. So it's not entirely obvious from this kind of scale how much bias there is. So just like one of the exercises we tried to do is to put this into, like what does this mean? Is this a large amount of bias? Is this a small amount of bias? So let's just take that, that line all the way on the right, that's the 2% line. So these are to the right of that line, people are getting fast-tracked into the extra help program. And so you can see that, there, like everywhere else, black patients are having, worse health, given that they're put into that program than not. We do a bunch of tests to make sure that this isn't just endogenous to the program effect or something like that. So lots of appendices in the paper to leaf through. But that fast track, that high-risk group today, or when we studied the program, that was 18% black. And the base rate is 12%. And so I think this already illustrates something that you know, but sadly, many other people don't, which is that a lot of people use this like composition as a measure of bias. And by this measure of bias, you'd say like, oh, well, this algorithm is overrepresenting black patients by 50%. This is great. This is not biased. This is great. But that doesn't tell you, there's no normative statement there besides like, are we randomly drawing people? Is that the counterfactual? So this doesn't tell you anything about who should be in the program. This is just saying, okay, 18% versus 12%, but what should it be? So to answer that question, what we do is basically like, let's zoom in on this threshold. And basically like, if you just imagine people waiting in line, and there's like a cordon, and so the people ahead of the cordon are getting into the program, and the people behind the cordon are not. We're basically just gonna find the healthiest on this measure, the y-axis measure, the healthiest white patient who's in the program. We're gonna pull him out of line, and then we're gonna take the sickest black patient who's not in the program, and we're gonna swap them. And then we're gonna do that again, and again, and again, until we draw two patients whose health is the same. So we want the marginal person, black and white, to have the same health after we do this swap. And we're gonna just do that again and again and again. And that procedure would more than double the fraction of black patients in the program. So it's basically like, instead of you drawing this vertical line, we're gonna draw a horizontal line and equalize the marginal patient's health on this measure. That procedure is dramatically increasing the fraction of black patients in the program. And I think this is a good, it's not the only way to figure out what should be the case, but it just does give you a sense that this is not a small amount of bias. It's underrepresenting black patients in that high-risk group by over half relative to the health needs. So this is not an artifact of the particular measure of health that we chose, that number of chronic condition exacerbates. So we can zoom in on a bunch of biomarkers, like actual health measurements. And so and all these graphs are algorithm score on the x-axis and the health measure on the y-axis. And there's a huge blood pressure difference between black and white patients conditional on the algorithm score. So if you look at that high-risk group and you look at the blood pressure difference between black and white patients, it correlates to about a 12% increased risk of heart attack. Diabetes, we use hemoglobin A1C, which is a biomarker of how bad and uncontrolled your diabetes is. That black-white difference correlates to about a 25% difference in all-cause mortality at 1 year. Anemia, cholesterol, it doesn't really matter what you look at. All of these biomarkers are very, very different in that high-risk group when you compare the black and white patients. So this is not an artifact of a particular measure of health. And in fact, when you triangulate across all of these measures, whether they are diagnoses or biomarkers or vital signs or whatever, the same pattern's there. So there are these huge differences between black and white patients at that margin where people are getting into the program. As fast-tracked. Any questions on these measures or definitions or anything like that?
Yeah. Could you explain again how you do the swapping?
Yeah. So basically, like the dilemma is, okay, today we've got these two populations of patients. One is getting into the program and one isn't. And we want to understand for the people who are getting into the program, we're seeing these, like if you just separate out the black and the white people, the black people look much less healthy than the white people, but they're both being fast-tracked into the program. And so the intuition is basically like, well, there are these healthy white people who are effectively cutting in line ahead of sicker black people that are not getting into the program. And what we're trying to do is basically like reconstruct what would happen is if instead of using this algorithm score, we just ranked people according to their health needs, and chose them based on that rather than the algorithm score. So that's that swapping procedure. It's basically swapping in and out of the program until you get people who are more homogeneous in health in terms of their health needs, rather than this other object, which is the algorithm score. Does that help?
How did you get the health needs numbers?
So those were from the electronic medical record. So the score is sitting on the server of this hospital system. And alongside that, you can link it to these counts of like the diagnoses that happen over that next year. And then you can also link it to all of these biomarkers, which are all living in the same place. And so it's a very nice setting to study these kinds of problems because of the richness of that data. It's all just living in the same place. Yeah? Do they opt in? So they're approached by the healthcare system, and the approach is like, would you like access to all this extra stuff? And so then they generally say yes.
Does the algorithm have access to the same features that you use, like here in OneDrive?
No. So the algorithm had access to the financial transaction data, which we also have access to. And so, for example, the measure that I showed you before, the main measure, this one here, this is basically like there's an analog to this in what the algorithm developers had access to, because this is just a count of the number of diagnoses that someone has. They do not have access to all of the other stuff, all of this stuff, because this is an electronic health record data and not in the financial transaction data.
Okay, so I mean, as a follow-up, the question was like, if we control for features, if we give them the same features, would the algorithms still show a bias? Like,
let me come back to this in a second, but yes, because, and I think if I can kind of caricature a little bit what you're asking about the right-hand side, like what are the predictors that the model had access to? And those are definitely different. The bias in this case, as I'll show you, came from a different source, which was nothing to do with the features that the algorithm had access to, and everything to do with the target at which the algorithm was aimed, like the objective function. And so let me try to convince you of that in a second. So how did this happen? Where is the algorithm going wrong? Is it because we see more about the patient than the algorithm manufacturers? One important clue about where the algorithm is going wrong is where it's going right. So this graph, again, is showing you the algorithm risk score on the x-axis. But now on the y-axis, instead of a health measure, I'm showing you cost over that next year, and it's on a log scale. And you can see that unlike the previous graph, here the black and white lines are overlaid very nicely. And so the algorithm is predicting cost. It's predicting it very well. It's on a log scale. And is predicting it in a basically equal way for black and white patients. So that's, I think, the key to this whole, to unraveling this whole source of bias, is that the algorithm is doing exactly what we asked it to do, which is predict cost. And it's predicting cost very well for black and white patients alike. And I think this is, in some ways, surprising, but in other ways, not at all surprising, because this is what the algorithm developers of this piece of software and every other piece of software that's used for this purpose, this is what they do. They total up the costs, and they predict them, and unsurprisingly, the algorithm predicts costs very well. So how do we put these facts together? Well, side by side, the only way to solve this mystery is like now we're looking at on the x-axis, instead of percentiles of algorithm score, we're looking at percentiles of health. So this is analogous to our resampling exercise where we switch out the healthier white patients for the sicker black patients. Now we're ranking everyone by health, and we're looking at cost. And you can see that conditional on health, and again, this is not sensitive to the particular measure of health we use, white patients cost more. So any basket of illness, number of illnesses, however you want to total it up, and it's about $1,000 difference on average per year between black and white patients.
But this is predicted costs or past costs?
This is predicted. So this is over that next year. Instead of looking at what happens to their health, we just look at what happens to their cost. And so that's the pattern we find. And this is a fairly old fact in the literature, but it's one whose implications for algorithms had not, I think, been fully appreciated. Yeah.
Does the cost, does the model treat name brand medication differently than the equivalent generic medication?
Yeah. Oh, well, it treats them differently in the sense that they cost different amounts. So that's one of the many, many differences that's going to be rolled up into this aggregate measure. And that's why cost is so weird as a target for the algorithm. It's because two patients are getting the exact same compound. One just prefers to pay a lot more for that compound. That's going to change how the model views the need of that patient. And weirdly, it's going to look at the more privileged person who's choosing to pay more for a medication and say, oh, that person needs more. I'm going to rank them higher.
But if they hit their deductible, they're not paying more out of pocket for it necessarily.
Oh, this is an out-of-pocket cost. This is total cost, for the payer. Yeah, so this is their total cost. It's not parsed out by what the patient's paying versus what the insurer's paying. It is just the total cost. Okay, so this algorithm is biased for predicting health, unbiased for predicting cost. And that is the case because black and white patients have a very different relationship between health and costs. For two rich and kind of voluminous and tragic buckets of reasons. One is just very different levels of access to the healthcare system. So strikingly, all these patients were insured, either Medicare or good private insurance. And despite that insurance, there's still lots and lots of ways in which finances can intervene or life circumstances can intervene. If your job is inflexible, it's really hard to, if you work at a big box store and your schedule isn't posted until a day in advance, it's really hard to schedule doctor's appointments. If you don't have someone to watch your kids or don't have a place to put them, so all of the ways in which poverty just makes life hard in general makes it really difficult to access healthcare, even when you have insurance. And in addition to that, we also know from a big literature that doctors treat patients differently. There's a really nice study that has a vignette of oh, this is a 65-year-old female with chest pain who has a history of this and this and that. So they present this to cardiologists, and they ask the cardiologist, would you refer this patient to catheterization to figure out if they're having a heart attack? And they randomize a picture of a black or a white patient. And even though all of the unmeasured things should be worse in Black patients, the doctors are less likely to recommend Black patients for advanced testing. So there's just all of these ways in which we treat patients differently. And all of that racism built into the system translates into lower costs. And so conditional on health, Black patients just cost less, which means that if you train an algorithm to accurately predict cost, it is going to be biased for predicting health. So this mechanism of bias, we called it label choice bias. And I think that, where does it come from? Well, it comes from a very understandable place, actually, because we want to identify patients whose health is going to deteriorate so we can help them. But that's kind of easy for us humans to say. Like, you know what I mean when I say health. Like, you have this web of associations, and it's rich and it's complex. An algorithm does not have that. For an algorithm, it's like, there's a variable, it's cost. It doesn't know that you don't literally mean cost. It's very literal. And it doesn't know that it's like, oh, sure, it's cost, but as a measure of health. Yeah, it doesn't know that. And so that choice of label, that process of converting an abstract goal into a particular objective function instantiated in a particular data set at a particular time, that is a huge and like a very dangerous area, and one that needs a ton of thought. But unfortunately, it's one that's usually made very expediently by people who are building these algorithms. And again, this is not, it's kind of understandable, because what is health? If you look at the definition of health according to the World Health Organization, very unhelpfully they say, health is more than just the absence of disease. It's like, okay, what is it? How do I measure it? How do I predict it in this data set? No help there.
So I agree with everything you're saying, but it occurs to me that here, it may well be that what the insurance company is trying to optimize is their bottom line. So if you're trying to sell software to the insurance company, and I'm not sure the label was an afterthought. It might be quite intentional.
So let me come back to that in a second, because we actually had some interactions with the company that made the algorithm, and so I have some anecdotal evidence that that's not the case. But from a kind of more principled point of view, if the intervention, if the decision that was being made on the basis of the algorithm was, I'm just going to turn down cost reimbursement for these people, then you could argue that yes, even though they pay lip service to health and whatever, if they're just cutting reimbursement for high-cost people, then you could argue that, yeah, the true quantity of interest is actually cost. In this setting, though, what's being allocated? What's being allocated is fundamentally something about health. And specifically, it's about preventing exacerbation of chronic conditions. They only save money if they actually prevent someone from ending up in the ER from a heart failure exacerbation. And so from that point of view, it's always a little creepy when Zoom is like, hello, I'm doing stuff in the background. Okay, so I think that's why, for me, the true quantity of interest, even if you were a profit-maximizing insurer, you actually still care about finding people whose health is going to get worse, because the only thing you have to do about it is to improve their health. You can't just slash their reimbursement. So anyway, but I'll come back to that in a second. But have I convinced you at all that that's not the thing they were actually optimizing?
You have convinced me partly. I still think that as the insurance company, if I know that if the white patient who develops a chronic condition will cost more than the non-white patient who develops a chronic condition, then I may prioritize.
Yep, absolutely. Yeah, I think that's right. But, I think that's very far from what this algorithm is doing. And so I think, in that high-risk group, there are lots of people who end up they have a knee replacement. And it's like, okay, what can I do about that? It costs a lot, but I can't do much about it. Okay, so I think, where do we go from here? I think one way that you could read this study is basically well, the bias doesn't come from the algorithm, it comes from the data. there's this bias built in to cost and access and all these things. And so I think it's a very short leap from that observation to saying like, well, it's like, this is why we can't have nice things. It's because, well, you want algorithms that are fair. But algorithms are unfair because the data are unfair. And data are unfair because society are unfair. And so until we fix that problem, we're not going to get fair algorithms. And I think there's a kind of a lot of pessimism, I think, in the literature. And I think I'm a little bit more optimistic than most people, in part because of the experience that we had after making this observation. So, cost is not an unreasonable proxy for health. Sick people actually, cost more, and that's true for black and white patients alike, but cost is this bias proxy. But given the richness of the data that we have, predicting cost is not the only choice. So you could very easily imagine going through each of these costs in a very detailed way and just making your guess about like, well, what's avoidable cost versus total cost? It's like, why are we, imagine a diabetic patient who's like, supposed to be taking insulin. In one world, they're taking their insulin every day. Insulin is expensive. That generates money. In the other world, they don't take the insulin at all, but then at the end of 2 years, they end up needing to get a foot amputation because they haven't taken it. That's also expensive. Why are we treating these two types of costs the same way? We're just bundling them up, and it doesn't make any sense. So you could easily imagine just going through that exercise and saying like, okay, well, these costs are, at least according to my domain knowledge, attributable to something that I could do something about, versus costs that are fundamentally good and like that I don't want to do anything about. I don't want to stop someone from taking their insulin because the insulin is expensive. That's a cost I don't want to control. So what we did in the paper, and I'll just kind of go through this quickly because it's not that interesting, is we just trained on these alternative labels. We compared it to training on the total cost label and came up with two fairly obvious points, which is that all these things are correlated. Like cost and avoidable cost are correlated, cost and health are correlated. So it's like they all kind of predict each other because they're all correlated. But because those labels have very different correlations with race, the implications for the fraction of, for example, black patients that end up in that high-risk group are very, very different. So if you predict cost, you end up with 14% black. If you predict health, you end up with 27% black. So they're all correlated. They're all kind of orbiting around the same thing, but the fairness implications are very, very different. So I think I just want to, this hopefully is obvious, but this is a very different mechanism of bias from most things that people talk about in the literature in general, but really in the medical literature in particular. There's a huge amount of attention to whether algorithms are using race or not in medicine. And this algorithm didn't use race as a predictor, didn't stop it from being very biased. There are many predictors that do use race that predict better than the equivalent predictor without race. So it's just, there's a whole like focus on that particular thing in medicine that I think is probably counterproductive. I think there's also a lot of attention to underrepresentation of minority groups in the training data. And I think that also was not the problem here. You could retrain the algorithm, with more or fewer people of different groups, but if you're predicting cost, it's going to have the same problem. And I think what Guy, you alluded to is like, was this a deliberate trade-off in design? Is the insurance company kind of an evil genius that's just like, no, they're not an evil genius. I think this was just an error. It was the way that we asked the algorithm to answer this particular abstract question and the way we formulated that problem. Okay, so I've got 15 minutes left. So why don't I think since the framework is in a paper that's easy to read, but this other stuff is not really, I'm going to focus on the lessons for fixing bias and probably skip the framework. So before we published this paper, we did a lot of reflection on like, well, what is the change in the world that we wanted to see from publishing this paper, besides, a good line on the CV. And I think that what we realized was that like there was one world where the company that makes this algorithm learned about it, when it was published and there was like some media attention and they were like on the defensive. Or there was a world where like we actually just like contacted them and were like, hey, we found this problem. And so we did that one. So kind of just like worked through our networks and figured out like, okay, who do we know that knows someone who's on the board of this like very large company? And it was a little bit nerve-wracking because we hadn't published yet, we hadn't even submitted the paper yet. And there was like some chance that basically like, we talked to some people at the healthcare system and we're like, we're allowed to publish this, right? And they were like, yeah, I guess so. But I'm sure an enterprising lawyer could have found some problem in what we were doing and prevented us from publishing in some way. But instead, the company was actually super responsive. Like, they emailed us back within like 15 minutes and they're like, we'd love to talk more about this racial bias that you found in our very widely used algorithm. And so they basically put us in touch with the technical team that built that algorithm, and they replicated our results in their data. So they found the same thing that we found, unsurprisingly. And they were very motivated to work with us to fix this problem, which they kind of identified as a problem. And so we basically just worked with that team. We said, okay, well, let's try to figure out like what are the labels that are closer to the thing that we're all trying to do, which is figure out who's going to have a chronic condition exacerbate, who's going to need help. And so we basically just used their same data set, their same pipeline, same features, same everything to retrain on a different label. So not cost, but a basket of things that was analogous to like that set of diagnoses and some other things that they had. And so by the metric of bias that they chose, which is not my favorite, but whatever, it's basically just conditional on score. What is the aggregate difference in chronic condition emergence by race? Like the original had about 50,000 of these excess chronic conditions conditional on algorithm score in Black patients, and it dropped by 84% with this retraining of the algorithm on a different label. So I think finding better proxies, going through this process of triangulating, really trying to understand the context, the decision, like where the harm comes from, I think that's a very, very high value activity for people to engage in as they not just seek to understand where bias comes from, but also kind of lay out a path for doing something about it. So I think a couple of lessons that we took away from this. One is that this would have been very easy to miss, and I wanted to flag this in particular for you, because had you taken the algorithm's objective function at face value, you would have missed this whole thing. So you could have run all sorts of calibration exercises on cost and whatever, like it would have passed many of those tests with flying colors because cost predictions were fundamentally good and fair. What was unfair was the choice of cost as a prediction. That was where the unfairness came from. So you almost have to start by, like not taking the frame of the algorithm as given. That frame is net of a value system and a set of choices and a orientation to things that are convenient and easily available. And all of those things can be deeply misleading. But if you find yourself in that local frame and not in this global perspective of like, well, what should it be predicting? What is the goal of this algorithm? You can get very easily misled. And the proof of that is that like, no one really caught this problem. The people who built the algorithm, you could say, well, they're an insurance company. It wasn't a very diverse team. But this company sold the product to a bunch of people at big hospital systems in their population health management groups, which were very diverse, very committed to equity, to like patient health, to all these things. Like they didn't catch it. The doctors didn't catch it. So we have an analysis, as I mentioned, like this human in the loop thing did approximately nothing to fix this problem. Patients didn't catch it. So this is a very hard thing to catch. And a lot of the common correctives, like the corollary of that is that the common, not common, but the things that you read about in the literature, it's like, oh, well, we need to orthogonalize all of the predictors against race. And like doing all that stuff also would not have solved this problem. The problem was the thing that the algorithm was predicting, not how it got there.
I'm very curious about this. This is fascinating.
Thanks.
And Some of the people who wrote papers that you're citing have talked about specifically the problem of having the wrong outcome proxy, especially in the context, say, of rearrest rather than violence. So, who's not talking to whom? What happened?
I think.
You agree, it is the same issue.
Oh, it's exactly, yeah, and I think that this is so general. It's like, we're almost never predicting the exact thing that we care about. In health, it's like, well, we don't have a variable called health, so we have to like do all this other stuff. In criminal justice, we're interested in criminality, but what's criminality? We have these variables called arrests and convictions. In finance, it's like creditworthiness. Well, what is that? Well, we have this income variable, we're gonna go with that. So I think that it's not that these facts are not known. Like there's literature in health going back to the 70s documenting, conditional on X, huge cost differences between black and white. We know that arrests are biased. We know, so I think it's that the knowledge needed to do this is not siloed. So I think that if you're in a data science frame, you're not thinking about structural racism and how that affects the measurement of different health conditions. You're just trying to get this data cleaned and the people who know these facts don't talk to the people who are building the algorithms. And so I think that there's this interstitial, this connective tissue between these things that's just missing. And I think part of that is because these this knowledge is locked inside of groups that don't share a language or an interface with the other groups. And so there's no, these groups are all just creating these things that are creating problems for other groups, but there's no one internalizing all of those externalities that come up. So I think it's a cultural problem and it's a language problem maybe. I just think it's very hard for data scientists to say well, what does structural racism mean for how I measure these variables? And it's very hard for, the people who know a lot about structural racism to understand okay, well, how do I convey this point in a way that this person will understand? So it's not a very good explanation, but I think that's probably my best guess.
So all of you, of course, be the counterexamples. Be the people who are studying algorithms and machine learning and data science and know something about structural racism and what to look for. You've seen a couple of examples earlier. You've seen this wonderful presentation. You have the video recordings that we'll be talking about this afternoon. So be the counterexamples.
Yeah, thanks. I really agree with that so much. And I think that, I'm not a particularly technical person, but even I can see that, I think by going very deep into one instance, there are a ton of really interesting technical things that come up. So I think there's this very superficial analysis that we did about correlations across these different labels and correlations with race. I think that's a bunch of very interesting technical stuff could come out of that. I think a lot of technical depth can come out of deep engagement with the content and with the setting and with the particularities of the decision, rather than starting with the technical stuff and trying to write a technical paper before you've gotten into the details. I think there's this sense in how does science progress? I think our stereotype is well, I sit down and I think about stuff and then I go and I do it. But most often in science, applied problems generate huge theoretical advances. And so I think there's an argument for spending a lot more time on these applied things and in real settings, dealing with real decisions rather than toy examples. To continue on that theme, I think bias can only really be defined with respect to the real world and the consequences of bias for real outcomes. And to illustrate that, I want you to just think about a hypothetical example where, and this is related to Guy's question. So let's say that the same algorithm is being used, but instead of being used by the hospital's population health management department, it's being used by a different department. It's being used by the accounting department, because there's an insurer or if it's in the hospital system, you need to have a certain amount of cash on hand to pay your suppliers so that you can remain solvent and have cash flow. So you actually just really need to know how much people are going to cost in your population. So in this example, we're not using cost as a proxy for anything. Cost is literally the thing we care about. And so this same algorithm is unbiased for this use. The last thing we'd want to do is start adjusting things for black-white differences because you're going to make hospitals that serve black patients insolvent. So the same algorithm is biased in one setting and unbiased in another setting, and the only way that can happen is because it's not an algorithm that's biased. It's an algorithm used for a particular decision that causes a particular harm if it goes wrong. And to be a little bit more optimistic, so we got a lot of media coverage for this paper. We were even in Breitbart had a story about this paper, which is hopefully the last time I'll appear in Breitbart. And we came up with basically a framework for doing a bunch of the applied follow-up work that kind of came in after that. So a bunch of people came to us and were like, oh, we're worried about bias in this algorithm. Can you help us understand if it's a problem? We did a lot of work with other health systems, insurers, some tech companies that were selling algorithms to health systems, and then also with law enforcement and federal regulators. And I think the framework that we kind of used for this and tried to kind of get other people to use is basically, okay, for a given algorithm, let's figure out the actual target that the algorithm is predicting. In this case, it was costs. Is that at risk of bias? Yes, because costs are not fair. They reflect access. They reflect differential treatment. So what is a new target that we could come up with that might fix some of those problems? We have a paper that we're finishing up now on bias in the triage system that every emergency room in the country uses to determine who waits for care and who gets fast-tracked back, because that is a judgment about resources that person is going to consume. All these other, it is just striking how we've basically found bias everywhere we've looked, but because of the richness of health data, we've also found ways to fix that bias and to work around it. And then back to Cynthia's point, I think we're often in this position of wanting to measure or predict some abstract thing, but our data sets contain only proxies. And I think it's very analogous to what happens to humans when you turn a measure into a target and humans optimize to that target. Algorithms do the exact same thing. They don't know that cost is a proxy for health. They're just predicting cost. Okay, let me break there. I think we're breaking for half hour. Okay, perfect. And then we'll come back and do building better algorithms.